Hello everyone, my name is MacTavish. I'm a master's student at the University of Calgary. I will be presenting my work called Perspective Charts, co-authored by Katayoon Etemad, Faramarz Samavati, and Wesley Willett. The volume and variety of data available worldwide has evolved rapidly since the invention of the internet. Bar charts are still one of the most commonly used data visualizations today, as they are simple and easy to interpret. However, bar charts are not perfectly suited to every type of dataset. For example, datasets with a large range with important variation at multiple scales presents a unique visualization challenge. Examples can commonly be found in population data, as shown here. A linear mapping between the range of the data and the height of the viewing space can result in undesirable compression of the charts, which makes differences between smaller values less readable. One potential solution is to use a nonlinear mapping, such as a logarithmic function. However, this type of mapping is difficult to read and understand in comparison to simple linear mappings. So how do we find a more natural solution to mapping datasets with large outliers onto a small viewing space? We propose a new technique that uses perspective projection. Perspective contributes to human perception of information. The concept of size constancy explains that the perception of an object's size does not change with the object's distance from the viewer. This is true even for two-dimensional representations of three-dimensional scenes. We use this feature of perception in the design of our perspective charts. We propose 3 novel data visualizations that use perspective projection and size constancy. Our first design, which we call the slanted perspective chart, shows a bar chart that is slanted backwards from the viewing plane, such that it is viewed in perspective. As the lower part of the graph appears closer to the reader, small values in the dataset become larger in comparison to a traditional bar chart. We use a simple 3D environment and predefined camera orientation for this design. The main problem with slanting a traditional bar chart is that large values in the dataset become compressed due to the perspective projection. This may make large values more difficult to read and compare. Our next chart, the stepped perspective chart, is designed to address this issue of scaling large values while also improving the readability of small values. In bar charts, space in some parts of the chart may be wasted due to large differences in values or outliers in the dataset. In these datasets, we can identify clusters of data separated by transitive regions. We can reduce the amount of wasted space by visualizing the transitive regions in an extreme slant. Each bar's value is still measurable in an area that is perpendicular to the view. This technique is comparable to traditional broken axis bar charts, which also address issues associated with large gaps between values in a dataset. However, broken axis bar charts have been shown to negatively affect the perception of scale in datasets. In the stepped perspective chart, the transitive region is still visible and the reader is able to perceive the approximate size of the gap. Our third perspective chart, called the circular perspective chart, is inspired by the impression of looking up at tall buildings and skyscrapers from a low vantage point. The horizontal axis of the chart is mapped to a circle, with the vertical axis extending away from the reader's view. This chart occupies a consistent viewing space regardless of the scale of the data or the number of entries in the dataset. Now that I have introduced our 3 visualization designs, I will describe the user study that we have performed. The study quantitatively measures the accuracy and speed with which users perform a series of tasks with various chart types. We also collected participants' opinions of the 3 types of perspective charts in a qualitative study. In our user study, we describe one hypothesis per perspective chart design, based on the concept of size constancy. The details of the study design are described in our paper and are available on the Open Science Framework. When comparing perspective charts to traditional chart types, none of these comparisons showed a significant difference in accuracy rate or task completion time for any of the evaluated task types. This suggests that due to size constancy, the use of perspective did not impact participants' ability to visually interpret values. As with the slanted perspective chart, the stepped perspective chart showed no significant difference in accuracy or timing compared to the traditional comparison method, in this case the broken axis bar chart. However, participants were able to complete certain tasks significantly more quickly and accurately with the stepped perspective chart than with the scale stack bar chart, a recent state-of-the-art design proposed by Willett et al. The circular perspective chart's comparison fixed viewing space visualization, the radial bar chart, showed significantly higher accuracy than the circular perspective chart for sorting and value retrieving tasks. Participant feedback about the circular perspective chart was also mixed. Some participants indicated that for larger values, the bars became too severely compressed in the circular perspective chart. However, participants also felt that the design was impactful and may be appropriate for artistic visualizations. In conclusion, results of our evaluation indicate that the use of perspective projection in data visualization is worth further examination. The slanted and stepped perspective charts particularly merit more in-depth evaluation as alternatives to existing chart types. Participants also felt there was artistic value in the circular perspective chart. Therefore, charts that utilize perspective and size constancy can be a viable alternative to existing visualizations. This concludes my presentation. Thank you so much for listening.